Hello, everyone. Yeah, hi. I'm Ravi. I'm a machine learning engineer at Intel. Today, I'm going to introduce you our Intel Nervana solution stack, so that probably you could use our technologies for your physics research and a lot of good stuff. So I'm going to just introduce you the technology, the hardware we have, and the software that is available right now. So Intel Nervana is a full stack solution to deliver solutions based on different frameworks. So users can import their data in multiple formats, any of these, and then build, train, and deploy solutions either on the cloud, which is has full multiple GPUs and hosted on Amazon at the moment, but soon we would be moving to a Nervana ASIC that's developed specifically for solving deep learning primitives. And the frameworks, Neon is one of the frameworks that is developed initially in respect to have very scalable and fast primitive implementations. And later we started developing MKL-DNN, and these primitives have been introduced into many other frameworks, so soon that will be available on the cloud. And also the solutions are provided on-premise deep learning appliance, in which currently we are providing with Knights Landing and Knights Mill processors, but soon that will be upgraded to Nervana ASIC as well. So Intel currently has like a end-to-end solution for AI compute ranging from spanning from data center to other edge devices. The data center, so some of the Xeon processors can be used for on the data centers for inference training, also at the gateway and also at the edge. And few of the Xeon 5 processors are targeted only for HPC workloads, or specifically with high compute and memory intense high memory compute bound applications. The Xeon 5 processors currently are like Knights Landing and soon Knights Mill. And also there are FPGAs which are like optimized for very specific workloads. That with the advantage of FPGAs is of course low power. And finally, the Crest family that will be released beginning early next year. This is specifically designed for deep learning only. I'll let you more details into the Crest family. So this has the compute units are mostly multipliers and memory, and there are no elements like cache which are required for graphics processing, but we do not need it for deep learning. So removing such unnecessary elements and then having only compute and memory enables to have unprecedented compute density, and also that has orders of magnitude more compute capacity than regular CPU or GPU. It also has isolated pipelines for data management and compute. So with that isolation, the data is always available to the compute. So you can reach theoretical peaks in computation. Also, the memory technology, the current memory technologies are not on par with the speed in which the compute requires. The ASIC has a new memory technology like high bandwidth memory technology with like 32 gigabytes of onboard. So there's no delay in getting the data, and since there's like isolated pipelines, the compute always can read at around 8 terabytes of memory access speeds. And also there are the built-in networking within the ASIC with 12 bidirectional high bandwidth links provides the movement of data at high speed, and also within the ASIC and also across the chassis. So the scalability and speed are highly enhanced. Coming to the software, Intel MKL contains DNN primitives and a lot of other linear algebraic functions, whole suite. But in specific to deep learning, not all of the math libraries are required. So Intel recently outsourced or opened up MKL DNN for collaboration with external communities. So any of the very specific deep learning primitives that have been coming up would be developed into the MKL DNN, which is open source, that enables us to rapidly iterate with newer DNN primitives. Most of the frameworks that we are working with are currently integrated with the Intel MKL. With these primitives rapidly increase or are highly optimized libraries that can run on CPUs itself. So these MKL DNN primitives are currently many of the basic functionalities like convolutions or ReLU pooling and specialized operations are used in ROI pooling, and Vinograd implementations are available right now. And these are integrated in many of the frameworks. Coming to Neon, Neon is a framework built is an open source library built on top of with specifically in terms of keeping in mind for an enterprise grade solutions for speed and stability, rather than few of the frameworks which have been developed through research for easy prototyping and experimenting. Some of the code has been the Maxwell, the GPU assembler has been re-engineered, and we've written like highly optimized CUDA kernels that actually runs much faster than CUDA in few of the benchmarks that have been completed by either third party as well. Python, the whole framework is written in Python just because it is much friendly, and the data scientists have much more access to rich higher libraries. And also this is primarily a kind of a glue language which enables to call underlying higher optimized primitives written in either CUDA or math kernel libraries. I'll just give you like a brief overview of how you develop a deep learning model in Neon. So you choose a backend. You can have multiple backends, like either you can run on CPU backend, GPU backend, or an ASIC soon. And then once you upload the data, you create your model architecture, and then you define your cost, and then you define an optimizer which runs on the training model. So there are several functions available in Neon as of today, and then this list is growing continuously. We are implementing multiple, as the research is catching up, we are implementing highly optimized code as well. So backends are like both GPU and CPU are supported, also soon the ASIC, and there are multiple preloaded data sets so that you don't have to worry about loading or downloading. If you have your own data set, you could, we have written a data loader which fetches in a highly optimized way in mini batches as well. We have multiple initializers, optimizers, activations, layers, different costs and metrics to actually visualize your detection rate or plot some pretty curves for understanding how the model is converging. So let me go through like a simple example. MNIST is like the hello world of deep learning. It's handwritten digits of like 70,000 images. The goal is to classify what the digit is. So here we write like a simple multi-layer Perceptron, where the input is like the 28 by 28 image pixels, and you have one hidden layer with 100 units, and the output is like 10 nodes, which I signify the probability of the digit being recognized. So first, in Neon, this is how you simply write. You generate a backend. You either choose CPU or MKL if you are using MKL, which is by default, or GPU. And then you load the data. We have several ways to load the data. Either you can use an array iterator, which fetches in batches, in mini batches. Once you load the data, you define your architecture, your topology, how many layers, or in this case we define, this is an MLP, so we are just defining a fine layers. And then the cost optimizer, the callbacks, in which you can specify during training what kind of iterations and model evaluations can be performed. And then you train the model. Once you started training, you get metrics based on epochs. Once you get a misclassification rate, you can either reiterate or modify your parameters. Some of the simple command line arguments, all these is available on at the website here, but just showing you the simplicity of how to define several command line arguments here. You can feed in a YAML file or a Python file and then specify directly via command lines. Some of the visualizations can be plotted by just providing some of the parameters this way. We also have some of the models that the mission objective here is to develop highly optimized models for enterprises and business so that they could use it for speed and scalability. So there are several models already available in our model zoo. Here we are just showing an example of a segmentation segnet, and here you can see the speed up compared to Caffe. At least it's like 2 to 3 times of the regular GPUs. And some of the model zoos, so we do have a variety of models available. So if any of the new user is trying to start with a model, they can either fetch the pre-trained model and then start working for faster iterations. So in summary, Neon provides like a very easy to use Python interface to write your network, and also it is readily integrated with Nervana Cloud, where you can not worry about the hardware because hardware is taken care. And then also once you start using Nervana Cloud, and also once the ASIC is developed, the underlying underlying hardware is switched, and you can simply get 10 to 20x speed up. So Nervana Cloud, once you deploy, the whole idea is once you submit the Nervana, the idea is more of like, you could think of it like a scheduler. You write your script or develop your Neon code that that I showed you earlier, like an MNIST, and then just submit that Python file to the Nervana Cloud, and automatically you would it would schedule the job, and you would just get response. So it has two powerful interfaces, and Cloud is a simple command line interface where you can do all the operations like uploading a data set, training your model, visualizing, and also there is a way we could spin up a container and give you access via a Jupyter notebook. That is what we call as interactive mode, where you have access to a Jupyter notebook, and here you can simply write all your code or Neon code, and you have full access to this container. You don't have to worry about modifying or installing any Neon software, or worrying about the hardware. And then you can have a full access to the Nervana Cloud appliance through this Jupyter. Finally, I'm going to talk about Nervana Graph. So we are currently developing an intermediate representation, keeping in mind to isolate or to have loosely coupled between hardware and the software. So you can pick and choose any of your front ends, that is like any of your frameworks, write the code, and then this compiles into a Nervana graph that is a graph is like you can the set of operations like DNN operations. Whatever code or whatever framework the code you write in gets compiled into a Nervana graph, and then this Nervana graph is agnostic of any hardware platform. So based on the hardware, it would generate optimized kernels for any of the hardware. So you write once, and you can deploy it on any of your hardware. That I would like to conclude, and then you can learn more about more details about all the full stack at intelnervana.com, and take any questions.
Thanks for a nice talk. I was wondering, so you said it will be the ASIC solution will be shipping next year?
Early next year. Yeah.
Early next year. So in which form? I mean, how?
It's an add-on card.
Right.
So, yep.
So PCI Express add-on card, or?
Yes, but when we build the chassis, the interconnection between different nodes would be through multi-gigabit, like either SerDes or I don't think I can talk about more details, but it would be a multi.
It's some kind of appliance. This
yes,
is the model how you will ship it.
Yeah.
Okay.
But it will be an add-on card. Yeah.
Okay, thanks.
Google Cloud or the Amazon Deep Learning, the service?
You
also, I'm interested in the cost, the difference expected cost actually between the Intel Nervana service compared to others?
Are you talking about the cost?
So, yeah, two things. One is benchmarking. Do you have any comparison?
So the first silicon is not yet out, but based on the emulations, we see at least like 10 to 20x based on different models with respect to current GPUs. So that is what the benchmark I can tell about. We haven't run any comparisons with Google's TPU, and Amazon is hosting only on GPUs as well. And with respect to cost, currently we are like doing like a professional consulting, helping different businesses to start with deep learning solutions. So it depends on business to business on how many or based on the length of the engagement and things like that. So cost is not fixed. But once this is being deployed in either within Intel, once it's been deployed, I think more details on the cost will be revealed.
I just had a question about whether MKL is relevant for the ASICs. I noticed on your slide you didn't have like Crest as one of the targets.
Yeah, so for ASIC, we have an Argonne transformer, a separate assembly language for the ASIC specifically. So yeah, so it's not MKL. So that's the reason we plan, the Nervana graph helps us have different transformers. So GPU, CPU transformer is mostly MKL. GPU is CUDA, and distributed is like NDIST, and Lake Crest is the Argonne transformer. It's a different set of primitives. Yeah.
I'm just a little bit concerned about Intel putting in the effort with MKL if they then have like this line of Crest. Is it going to be that Intel still want people to run like deep learning on CPU, or they're going to be saying?
So it depends on. So there are two phases, right? Training and inference. So even for inference, this is like it's a massive compute power for training, but for inference it might be an overkill. Maybe we can run many batch processing for inference and things like that. In that respect, the Xeon processors or the Intel architecture would suit best for inference. And also training, if someone really doesn't care about the speed, but if they have existing clusters, which many of the data centers and research universities have, we need to support them. So that is the reason. Yep. Sure.
So what's the difference between the Nervana graph and the graphs that TensorFlow, for example, produces? There are similar the graph def. I would say more closer to a graph def of TensorFlow. XLA is much more very fine-grained, fine-tuned, or like very, very low operations. So we are here trying to strike a balance between the operations and the flexibility that the user is given. So that's different, but both have similar flavors, yes. But we are trying to strike a balance between flexibility and performance, because how low can you go? If you're writing operations at a very low level, then it becomes harder for the user to construct a graph with such low primitives. But once we go a bit higher, then the user might not have the flexibility or to define newer operations. So
we are trying to strike a balance between, because we cannot essentially write all the operations optimized for all the kernels. So we have to choose very carefully as the best deep learning primitives that encompasses everything. So yeah, but it is of similar flavor, but we are trying to strike a balance between flexibility and performance. Thank you.